All right. For one function. So why do we have functions? What's function notation? What are the parts of the function notation? All that stuff. So definition-wise, dependent, independent, also known as, well, the independent variable can be also known as a control variable. It determines what happens with the dependent variable. And in our world, usually, what variable represents dependent? Yep, and then the x is our control or independent. So what we're going to do is talk about functions, and functions are a set of members that have some relation to one another, and we have a specific set within a set. The function itself has to be a one-to-one relationship. So functions are within relations, and we're going to focus today on the function aspect of this, although you can graph both of them. You can graph just relationships where you have non-one-to-ones, and then you could also graph, well, we know we can graph functions, but functions are the ones we're interested in because these relate what the control variable is doing to change the outcome of the dependent variable. So this should be reviewed because we talked about all this stuff in Algebra 1 and Algebra 2. So we can represent a function in a graph, in an equation, in a table, in a word problem, just an application statement. You can have functions represented. So here we have a table, one of them being a function, one of them the other is not a function. And that is because, here's the big giveaway, when you are not a function, you're representing it as a table. When you're not a function, you should see repeated x values. So what happens here is I've got a value of x of 2 giving me two answers of y, and that's not one-to-one. And we could graph that thing still, but it just won't be a one-to-one relationship, which means it's not a function. We're interested in it's a relation. So we're going to focus primarily today on the equation part of this and the graphing piece of this. Although tables can be used to do graphing of any given function or equation, you can always pick your own x's. You always forget what the parent function might look like. Or if it doesn't have a parent function like a rational equation, you can always pick x's, find y's, and just make sure you're giving yourself negatives and positives and zeros and stuff. And then you can see what the thing's going to do. So that's always like your safety net. You can always fall back on that. Go to the t-table thing. So that's what you're doing. All right, function notation. Why do we use it? Can anyone explain why? Why might we use this whole y equal f of x thing instead of just saying y equal x? So I know what my x value is? In what sense?
Well, like x is just representation of what your original.
Okay, so then you're going to know your dependent is going to be as a result of that x? Okay. Let's think about, if I go back to chapter 1 when we were graphing our projectile motion problems, those were in function notation. How was it written in function notation? You guys remember that stuff? H of t, right? H of t. Height as a function of time. So what function notation is helpful for is instead of just saying y of x, where those are generic, we try to relate function notation using variables that refer to the control and the dependent thing, whatever those are. So height being dependent on the time that the object is in the air, we use h of t. So it's just a way of, I guess, giving more detail to the values that we're actually using to create this graph or to establish this equation. So that's the whole idea of function notation. Two tests. Vertical shows whether we have a function. You can have a one-to-one function, a many-to-one function. Horizontal line test determines whether or not a function will have an inverse. You guys remember that stuff? Inverse? Does that sound familiar at all? Switch x and y. Yeah. Yes, okay, good. We're going to be getting to that. Later on in this chapter, we'll talk about that. So these are two ways of graphically determining whether I have a function and if it'll have an inverse. All right, let's check out some problems. this concept of domain, remember we have two parts that we're considering when we're graphing. We have domains, which is all of the x values that create our graph. In the range, all of the y values that create our graph, all the values of y. Algebraically, we use that to find domains. Although if I have a graph visually, I can usually see domain and range. But if I don't have a graph to look at, we're going to be algebraically finding the domain. Domain. I concern myself with domain in terms of variables, values that I may not be able to be when I'm hanging out in the denominator. So when I have variables in the denominator, that is where I'm going to look to check out maybe what constraints there are on a domain. Maybe it can't be negatives, or maybe it can't be a 1 for some reason. So we're going to look at the denominators to find domain. If I had an x in the numerator, we could have negatives up in the numerator, we could have zeros in the numerator, we could have positives. All of that would give me a legitimate, real solution for g of x. But I can't have, like in this example A, what can't I have down here? What won't work? Not in this specific example, just with a variable in the bottom, what do I have to be careful with? I can't have something. 0. I can't have a 0 down there, right? And in this other problem over here, the square root one, specifically with even roots, what is it that can't be underneath the square root? Negative. So now those two constraints help me determine what my domains are going to be for these things. So without even graphing them, I can go ahead and find the domains of these functions.
X squared always all reals.
Yeah, good point. So this one really doesn't have a restriction, does it? This first one. You're right. Good point. But I would still, I'm thinking x squared plus 1 cannot be 0. So what we do to find domain is we pick the denominator, we set it equal to 0, and see if we actually find a value. And in this case, we find values, but they're just not real. And that's fine. If I don't have reals, that means, like Chloe said, x's can be anything because I can put a negative in there and get a positive. I put a 0 in there, I get a 1 on the bottom, which is still okay. And I get positives in there, and I get another positive. So in this example for A, because it's x squared plus 1, I would say that the domain of this function, I can put anything in for x, and I'll find a real value for y. So we're going to express domains. We're going to use set notation. So if you come from Precalculus, you've seen set notation. If you haven't, you probably aren't familiar with set notation. But there are rules, and then there are list forms of set notation. We're going to use the rule form primarily. Sometimes we use the list form. But this is the rule form of set. And what a set is it's a collection of items that represents, in this case, all of the values of x that generate a graph for this specific problem. Now we're going to use a brace, and then we're going to use this notation. We're looking for domains. We're talking about x values. It's g of x. That was g of t. This would be t down here. So x is such that, vertical line means such that. X's are going to be, in this case, all reals. Now we have a way of writing all reals with a symbol. And it's this. I call it a double barred R. So that is the set notation method of writing domain. We could use the same thing to write range. Probably more of a formal way. I kind of am a little more on the informal side when it comes to set. I'm okay, although we're going to try and do this, but this is also a description of the domain of this thing. If I were to write in inequality notation, x equals all reals, or maybe using interval notation, x would be negative infinity to infinity. So those are some different ways of writing domain. But we're gonna go with all right, so x can be anything for that graph, and it would create a value of g of x that is real. Everything's going to work. How about that other one over there? The square root one. We've already kind of hinted to the fact that it can't be negatives in there. So what do I do to specify that it can't be negatives for the square root of x squared minus 1? How do I write that? Okay, greater than or equal to would be meaning I can be positives, and because I can be a 0 under a square root, but why do I want to not be a 0 under this square root? Because then I'll be undefined, right? 1 over 0. So if that 1 over wasn't there, and it was just g of x equals the square root of x squared minus 1, well then I would say I can be zeros and whatever else is making me positives. But because I am hanging out in the denominator, that x squared minus 1 has to just be bigger than 0. I have to only be positives. I can't be a 0 because I make it undefined down. So this is like the stuff we just got through doing in chapter 3. That is a sign chart problem. I find my zeros, x plus 1, x minus 1. So my zeros are plus and minus 1. Set up my sign chart, negative 1, positive 1. I test where I'm going to be equal to a positive value, so if a negative 2 is put in there, I get a negative and a negative. If I put a 0 in there, I get a negative. If I put a 2 in there, I get a positive. And so I'm interested in anything from negative infinity to negative 1, but don't include negative 1. And then from 1 to infinity. So the domain of this graph, or this function, would say x is such that x is less than negative 1, or x is greater than 1, or maybe I want to use interval notation and I can just go negative infinity to negative 1, union with 1 to infinity. And there's all the values of x that will determine this. Yes?
Why did you forget about the square root sign?
Great question. Why did I forget about the square root sign?
It's not important.
No, it's very important. The square root sign determines that. If it was an odd root, cube root, I wouldn't care what's down there. Because I can take the cube root of a negative number. I can take the cube root of 0. I can take the cube, right?
Oh, so it just made that so it had to be positive.
It had to be positive. That's all I'm doing. So I know under even roots, I'm going to always have to be this, and in some cases, or equal to 0. So that's why it's just the radicand you look at. You don't need to, you can just ignore the radical at that point. Good question. All right. What other questions from that? No? All right. Maybe we have some time. We'll come back and graph these and actually see what they look like. All right. What about this guy? You want to try that one? What would the domain of that have to be? And while you're jotting that down, maybe we'll take a peek at the graphs of these real quick. Good idea to just do some review of graphs. Does anyone happen to remember parent function of a radical? What that thing looks like? How much of it? Half of the sideways parabola, exactly. So this is a positive, this is called the principal root. It's just positive like this. This is only the upper half of a sideways parabola. If that was negative square root of 1 plus x, I would be down on the lower side as a reflected half of the parabola. Yeah, good. So in terms of domain, though, How am I going to set this up to find the domain? What statement am I going to have to make for this? Anytime I have radicals involved, we got to think about this. What? I can't be negative. So I always think about if I have radicals that are even, can't be negative. So always set things up to be positives only. If I have denominators of variables, I got to think about can't be zero. Those are really the two main focuses for domain you guys have to be careful. Right? Can't be radicals, producing negatives, can't be zeros in the denominator. Yeah.
Well, then, we would guess it's very connected to the zero.
Could it be? Is that what you're asking me?
Yeah.
You mean that's the answer that you came up with? And wouldn't we want to say, though, that the radicand has to be greater than or equal to zero? Don't we have to say that?
Oh, yeah.
We'd have to say the whole thing has to be greater than or equal to zero, which means x has to be greater than or equal to negative 1. So it's a domain x such that x is greater than or equal to negative 1, and interval inequality notation. X from negative 1 to infinity in IB notation. Yep. Okay, we're gonna take a look at the graphs, see if we can get all three of these in here, all in the same one. Let's do this one since we're here, just to refresh maybe some graphing. If you know your parent functions, great. It just makes it speedy to graph things. You got to know what your start point is, or if there is no start point, some graphs have an imaginary start point like exponentials and logarithms do. You got to know where your start point is, and then you got to know what your critical movements are. You guys have done from Lockray or myself, Algebra 2, we talked about critical movements. So in a square root function, if the parent function was y equal to square root of x, your critical movements for this thing were right 1 up 1, right 4 up 2, right 9 up 3. And we got those because 1, 4, and 9 are perfect squares. If you take square root of them, we get the 1, 2, 3. So all of this would happen from, now we've seen this before. This equation or something that looks like it. Does that look familiar at all? Yeah, that's our generic. You notice the A and the H and the K. We've seen that already in vertex form for parabolas. I can use this with any function. The A has a purpose, it stretches and shrinks your graph vertically. The H has a purpose, it moves your graph left or right. And the K has a purpose of moving the graph up and down. So I can look at this 1 plus x, and I see that in this case, this is the same thing, if I switched it around. My h is a negative 1. So my hk, which isn't a vertex for square root functions, this is start point. My hk in this case is negative 1. Well, if we look at our domain, that's where we start, at negative 1. So I go negative 1, 0, and then right 1 up 1, right 4 up 2, right 9 up 3, and there's that graph. Let's go look at the other ones. They're not so obvious. Oh, before I do, the questions here on that, they didn't ask us to graph it, but I figured, hey, why not do a little review? Yeah.
So if you're going up, you would multiply that by an A.
Yeah, so if there was a 5 in front of that thing, all of these y movements, 1, 2, and 3, would become 5, 10, and 15. But the x movements stay the same. All right, good question. Okay, let's just go peek real quick. 1 over the square root of x squared minus 1. We know our domain is going to be from negative 1 to the left and right from 1. These are not parent function type graphs. These are kind that I would put a t-table together, pick some x's, find some y's, type of thing. And I just want to make sure that I'm picking x values that one fit within my domain, and give me enough to see what's happening. So if we were to just put a t-table here real quick in this graph, just to see what we would get. Let's just start picking some numbers. What if we put let's do a -5. And how about a -2? Can't put a -1 in there because that's going to produce an asymptote situation. So we do have some asymptotes we have to consider this. Vertical asymptotes at x equal 1 and negative. What do you say, 0? Put a 0 in there, and let's put a 2 in there, and a 5. Now let's just see what we get here. So -5 squared root of 25, 25 minus 1 square root of 24 is going to be just shy of 5. So 4 point something, and it's 1 over 4 point something. 1 over 4 point something. I'm just going to 0.2 blah, blah, blah. And then if you put a 2 in there, 4 minus 1 is 3, and square root of 3 is 1 point something, and 1 over 1 point something is just shy of 1. So some 9 something or other. Put a 0 in there, I get, oh, got a problem there. What is it? Oh, thank you. Yeah, you guys give me some actual values. Why is it, I can't use a 0 because that's not in my domain. Yeah, I can't use a 0 because of that. All right, so what was this, Alex? 0.58 or 2? Does anyone have the answer for -5? Okay. 0.20. Okay, and then these are just going to be the same thing. 0.58, 0.2. And if I kept putting bigger numbers of x in there, you're going to see that I'm going to approach a certain value. It seems I'm approaching 1 over, like if I put 1 over a million, I'm getting close to 0. So this thing has a horizontal asymptote. We haven't really talked about this. It has a horizontal asymptote at y equals 0. So what does it look like? Well, it looks like this. It's got a horizontal asymptote there. It's got a vertical asymptote at -1, a vertical asymptote at +1. It's going to have some branch type of things. So what did we say? At -5, I was at 0.2. We're right about there. And then -2, I'm a little higher. And as I got close to that vertical asymptote, what I would see is my graph kind of does this. And that's called a branch. And on the other side, well, I have some stuff going on in between negative, or to the right of 1. It's the same thing. I'm doing this. And then if I put some stuff between -1 and 1 in there, I'm not going to get some, I'm not going to get answers that work. Yes, and certain, if the polynomial was different, or the rational equation was different, yes, I could have things in between this. All right, so you can see they're all different. You gotta have to put tables together for some of them if you don't remember the parent functions. Is that a hand back there, Zachary? Oh, yes, you're good. Yeah. All right, let's move on here. Just an FYI graph, right? Not really doing much with it other than talking about maybe a different way of looking at the graphs and how it helps you determine domain and range. If I took a graph and I were to I would draw vertical lines from any point on that graph and I go touch the x-axis. The points that I hit on the x-axis, or the range of points that I hit on the x-axis, mainly from here to here, those values determine your domain of the function. And if I did the same thing on the graph, but this time did horizontal lines and went back and hit the y-axis, those values would determine your range. So graphically, this is what we're doing. We're trying to find what is that interval between what and what that defines my y values and my x values. Now over here, why did we, on this example, why are we turned out for 1? Because it's an open circle, right? Remember that stuff? Open circles, we don't include that value. So for x's of 1, for y of x, or x of 1, y of 1, it can't be included, so that's why we have that. All right, so that's just a little visual on the whole concept of domain and range. Is that thing a function, first of all, that graph? Oh, look at that. See, I just changed my voice. You change your answer. Yes! It's a function. It's a function. Does it pass the vertical line test everywhere? Yeah. It passes the vertical line test. Now, if I were to ask you, does it have an inverse? Well, now we have a problem. Because an inverse function has to pass a horizontal line test. Give me a pin. So, like, if I went right there, I'm intersecting the graph more than once horizontally. That means I will not have an inverse. But anyway, that's stuff to come. Just giving you a preview of what's coming down the road. All right, let's do a little. Since we need the help with some graphing, this is always good to do this. Let's see if we can. You guys want to try these by yourself? I'd like you to try them by yourself first, and then we'll do them together. But we got these two graphs: y equal 4 minus x squared. And then another one, x equal the absolute value of y. Now, all this notation simply means is you're picking points x and y to fit within the given equation of y minus 4x squared. Don't let the notation scare you. It's just saying, I'm finding all of the values of x and y that would make this graph. That's what that's asking. Yes, Chloe?
Why is there y equals the square root of x?
Oh, great question. Why is there y equal the square root of x? I had been using that for something else, and I left it on there. So that's actually an oops right there. That should be it. But good catch. All right, so you guys, you want to buddy up, tag team, see if you can come up with the equations for both of these. And then we'll take a look at the domain and range. So here's what we have. First of all, we're going to make it easy. There's the graph for y equal 4 minus x squared. Now, how do we get that if I didn't know my parent function? I plug in x's. I put some negative x's in. I put some zero in. I put some positive x's in. And I would see this symmetrical graph around the y-axis. If I knew parent function, I recognize, hey, that thing is just a shift up. And it has an upside down because the a is negative. And I would use my parent function. Well, just finding the zeros is not enough to be able to graph a problem. I need the vertex. Yeah, there you go. For this case, yeah, that'd be okay. All right, so that one, not so bad. This other one, this b, this is a weird looking guy, and not a parent function. So we're gonna put in for b, we're gonna put in some values. So if I put in, and this is what the discussion that we were just having, if I try to put a -1 in for x, is there any way that I can take an absolute value of a number and get a negative answer? And the answer is no. So I cannot have negative x's because I can't take the absolute value and get a negative solution. So we're going to only be able to test positives and 0. If I put a 0 in for x, I get a 0 for y. If I put a 1 in for x, there are two ways that I get a 1. The absolute value of 1 and -1 would produce an x value of 1. If I put a 2 in, then I get a 2 and a -2. So we see this as a sideways t. So it's going to look like this. Oh boy. There we go. It's going to look like that. All right, now, the big thing in addition to graphing was also to find the domain and the range of these. So thinking about that parabola, every parabola in the world, if it does not have a domain restriction, will always have what for its domain? Everything works. A parabola keeps going right and left unless it has a restricted domain, and this one does not. So in terms of the domain, for A, we have x such that x is always. The range, now parabolas, they don't have the are either above or below their vertex. It depends on if they open up or down. So because this one opens down, the range would have to be 4 all the way down to negative infinity. So I'd say y, what's that? I'm just going to use this notation. Negative infinity to 4 would be the range for that. Everything below. The zeros, set 4 minus x squared equal to 0. It's a difference of 2 squares. So I find that my zeros for that function are plus and minus 2. And that would be what we have for A. Is the blue graph a function? Doesn't pass the vertical line test, right? So if the graph is a function, then we're finding the domain and the range. If it is not a function, we're not finding the domain and range of this thing. The domain, if we described all the x values though that made this work, we'd say everything to the right of 0. The range would be all reals, and it only has one 0, which is at the origin. So that would be the description of that. Questions on sketching some of these graphs describing domain and ranges for functions? Is this good to see a little practice on graphing? All right, how about down? We have 2 of them here. B's down here, camping out. Come here, B. Sketching the graph. Find the range, zeros. I don't know why I said just find the range. Find the domain and the range. All right, again, I'm going to pause here. Let you guys do some practice for graphing. Graphing the quadratic, we have standard form, so we want to find the axis of symmetry first. Negative b over 2a. Negative of negative 1 over 2, 1 half. Then we plug in f of 1 half to find the y. And we get 1/4 minus, I'm going to change everything to fourths. 1/4 minus 2 fourths minus 24 fourths, giving me negative 25 fourths. So my vertex, we'll go ahead and change it back to a decimal because we're going to be graphing it. My vertex is 0.5 and negative 6.25. The zeros, see, this should all be reviewed. X squared minus 6, factor it, x minus 3, x plus 2. So my zeros are 3 and negative 2. And really, that's kind of all I need. I can do my parent function movements. There's no stretch or shrink factor in this. So once I'm at my vertex, I can go left 2, up 4, left 1, up 1, so on and so on. So 0, a half, and negative 6.25. To the right, down 6.25, that's good. And then I'm going to cross at, what am I crossing at? 3 and negative 2. So my axis of symmetry, there it is, right there, right down the middle. My parabola is looking something like that. And it didn't ask for domain, but it would be all reals for this. It just wants the range. And in this case, my range is the vertex and everything above. So I would write range y such that we can include the vertex, negative 6.25 to infinity. The range for that one. And I think everyone was pretty good on that. This next one, though, is a piecewise function. It's just 3 linear equations. And all of this stuff, the u greater than, the u equal, the u less than, that just tells me how much of that graph I actually see. So what I recommend for folks if they're graphing these piecewise is you lightly draw in the entire function without these restrictions, and then you just erase the parts you don't know. You don't need. So I'm going to get rid of this. We can do this next one. So f of x equal 1 equals 1 of my, and then I have it equaling 0, and then it's equaling negative 1. So those are all just horizontal lines. So f of x equal 1, there it is right there. Right there. It'd be arrows on both ends. F of x equals 0, there it is. F of, horizontal. F of x equal negative 1, there we go. But I don't see all of that because now these restrictions on the domain tell me how much of the graph I actually look at. So for the first one, I'm going to grab the graph and I'm going to erase everything from 0 on. And that's going to be an open circle right there on 0. And then it's going to have an arrowhead going forever that way. The next one is actually just a point. So get rid of this. F of x equals 0, horizontal line, at a specific value of 0 means it's just that point right there. So that's what this one is. And then lastly, the next one, we're going to look at everything below 0. So same thing, concept-wise. Get rid of the right side of the line, bring it back, put an open circle on it, and point to the left. Is that a function? Fast vertical line test. There's only one value it's actually hitting when it goes through x equal 0. It's hitting at 1 right in the middle there, the origin. So that is a function. Then in terms of its range values, what would we describe the range for this? All reals? I don't know if I'd say all reals. Yeah, you're right. In the domain world, it would be all reals. But in the range world, we have y such that what? What do we got for range? 1 and 0. So it could be 1, it could be negative 1, but it could also be 0. So we can just write it as y equals negative 1, 0, 1. So there's my range. It's specifically just those values. Now you're going to have some of those homework-wise, piecewise things, and so again, no parent function for those. It's just a matter of determining what the equation for each of the pieces looks like, and then erasing the parts that you don't need to see anymore. All right, one more, just again as a sum it up. Domain and range. Now I have the graphs. Can I find from the graphs the domain and the range? This is the easiest part of it, probably because we physically can see what the domain is versus an equation where I might not be able to think about the shape of the graph and interpret that for domain and range. But these, I think, again, if you just think about taking all aspects of the graph and then dropping values of the graph down to the x-axis, that defines my domain. Doing the same thing horizontally, dropping values of the graph to the y-axis, that defines your range for this one. So, what say you? What about A? Who's got this one for me? What's my domain on this one? Greater than negative 2. You guys agree with that? Yeah, it starts at negative 2. There it is right there. And then everything, there's an arrow on the right. So, greater than negative 2. And then what's that, Clay?
I was doing IB notation.
Okay, yes. Then it would be negative 2, but don't include it. to positive infinity. Have you got a range?
Y is less than 6.
Very good. Can I be equal to 6? Yes, I can. I can be equal to 6, but I can't be... All right, so we got y such that y is less than or equal to 6. And again, you could write all these with the IB notation as well. That's fine. All right, and then the zeros, we only have 1. And it's right there at, what is that, 6? X equals 6. All right. Domain on B. What do we get to include? Everything. Range on B. What do we not get to include? Yeah, we don't get to include any negatives because I have a vertex point on the origin and the opening up. So gotta be careful on that. And then it has only one 0, which is hanging out at the origin. So 0 is the sole winner. All right, what do you think, guys? Difficult? Easy? So far, it's not bad, right? Yeah. Yeah, it's really at the end of the chapter that it gets kind of crazy. The beginning part's not that bad. All right. Any questions?